Welcome back. Today I will talk about Scikit-Learn. Scikit-Learn is a toolbox. It's a so-called API which provides machine learning tools and a large selection of data sets that can be used to train any machine learning algorithm. The benefit of Scikit-Learn is that you don't have to do your own coding. You can just use the existing library and select from a large choice of various approaches to analyze data. However, the downside is that Scikit-Learn is a bit like a black box, which means you don't really know exactly what is behind it. And many people, in particular in finance and business, that don't know much about machine learning, are using Scikit-Learn without any further reflection, which can be very, very dangerous. So I will show you how it works. I will show you in today's session how to load data and also how to use Scikit-Learn to train a perceptron. And finally, how to visualize your data. The benefit, I think, is quite clear, but let me also stress a clear warning here. If you don't know what you are doing and you just use blindly a ready-made package, it could be quite misleading. Very often in practice, the algorithms used are not helpful and not tested properly. So it's very important that you actually understand the mechanisms behind it. Good, let's get started. First of all, there are many different libraries we have to import. It will take me a long time to actually type it out, so I will just literally copy paste that. And of course it's already provided online, so please copy paste, otherwise I spend 10 minutes just typing it up and most likely I will have a few typos. Now the first thing I want to do is I want to get access to data on our Scikit-Learn, and in fact we already loaded the data sets in the first command on line 9, and now I use the API to access the data. An API is an application programming interface. So APIs are used very frequently to interact between different applications, for instance, to get access to data, and there are various useful uses of them also when it comes to financial data, for instance. So for instance, you can use Bloomberg, and if you know how to get access to the API, it can give you data straight into your application. Now I want to explore again the iris data, but again this is just an example. You can use any other data set, and I refer to data sets. Now this is a built-in class in Scikit-Learn. Dot to open up, of course, my dot operator, and then I load the particular data, and you see we have a large section of things you could load, and it refers to iris, and I just open close brackets because that's actually a method call on an instance. Yeah, so that would basically hopefully do it. I will just now test that and see whether this is working. You see, it takes a little bit of time because it has to connect to Scikit-Learn, and now we have a new object which is a so-called bunch object. So that is not a data frame we are used to like in pandas. Now these objects are different, they are structured differently, and they already come with a split between a target value, which is our y in our notation, so that's our output, and a data matrix which contains the inputs. So when we look into this, that's already a data matrix, In this case we have 4 dimensions, and you also note that the constant term is not part of this data matrix. So the implementation is a bit different compared to what we have done. So that is quite useful. What you also note is you have a target variable here, which you can access as well. So that's my target classification. Now we are at the moment treating this like a training data set. So these targets would be the observed targets which we obtain from a training data set. So that is good to know. So what we do next is we specify y, which is our output, and we just have access now using iris, which is our object, the so-called bunch object. We use the dot operator, and we have access to target. So that basically tells Python define y, and y should simply take the target variable, which is our output from the iris bunch object. So that will just simply give me the array as you would expect, and we have, as you can see, 150 cases. So that is quite a large data set. So that's a good start. Alright, it might be interesting to look into y a bit more carefully and to print out unique labels. It's just to provide an overview. Of course, you can actually explore it just by clicking on it, and you see there are 3 unique labels. However, this does not work in any IDE. So sometimes it's useful to explore this, or if the data is really large and not sorted, like in this case, it might be quite helpful. So I do a print function. I use quotation marks, and I just say, okay, class labels, and then I put in a comma, which simply is a separation in the print function, as we know. I refer to my NumPy library, and I refer to unique, which is a method inside the library, actually a function to be precise, and pass in y. So what this does is it looks at unique values in my array y. So if you run this, it should give us an overview, and of course, as expected, we have 3 different classes, different labels, 0, 1 and 2. So that is quite helpful. Now the next thing is we want to select a data set. Of course, we could use simply all the data in the data matrix, but as you have seen, that's a 4-dimensional matrix. Now the issue with that is it becomes much harder, of course, to visualize it. So I want to restrict us to only 2 dimensions. So I suggest we take the last 2 variables. Now there are different ways of getting access to that, but I define now my own data matrix X, and I refer again to the iris object, and then I refer to data, which is the data matrix stored. I take all the rows, so I put just the column here, I put a comma, which will then refer to the columns in my data matrix. Now there are 2 different ways of doing it. One way is to specify a starting column, which is column 2 in our case, and go to the end. So one could do something like that. You don't have to spend actually the end. You could specify an end, which of course is exclusive. So that would work as well. So there are different things you could do. So we can run this command here, which is an application of slicing, and you would see the last 2 columns would then be put into our own data matrix. Now what you could also do is you could get rid of this part here and run this, which should also work. That's another alternative. It's actually, this is better, it's more elegant. What you could also do, and that's a different way of approaching this problem, is you could pass in here a list. So you could, for instance, do something like 2 and 3. Now that is useful in particular if the columns you want are not in the right order. So sometimes that might be a better way of implementing it. But we just stick to the first way because we are focusing on 2 consecutive columns, and that is actually a very elegant solution for that. Okay, so that's a good start. The next thing, which is very useful in our Scikit-Learn, is to split the data into a training and a test sample. Now, a training sample, as we have seen before, is used to train our machine learning approach. The test sample is unseen data, so we don't know the correct labels. We use our test sample to check how good our algorithm is able to identify certain cases. Okay, so how can we do this? Of course, you can always kind of write your own code to split the sample into subsamples, but there's a very nice implementation in Scikit-Learn which is making things a lot easier. I will just type it out and then we talk about this. So what that does is it takes our data matrix and our output, so the target variable, it splits them according to my test size. So 0.3 means that 30% of my data, in total we know we have 150 observations, should go into the test data, and the rest, which is 70%, is my training data. And here you see the assignment. So we specify first what is training, then what is test in our data matrix and our output vector. We have a random seed in this case, so we have a random state 1. That is not really massively important. You could also skip that, but quite often it's nice to control the random state if you want to replicate your results. And then we specify stratify as equal to yes. This is not the best ever implementation, so in most other packages you would actually need to put quotation marks here, but that should actually work. Now what this does is it ensures that the same proportion of your labels is in your training and test data. So for instance, if you have 10% of positive cases and 90% of negative cases in terms of your label, the certification ensures that this proportion is exactly the same in your training and test data. Of course, now you can ask yourself, is this a good way of doing it? Quite often the answer is yes, because you want to make sure that you have a comparable data set. However, in practice, and this is the catch here, it's not very likely that the new data you observe is similar to the old data. But of course, whatever you do in machine learning, as you also do in statistics, there's always an implicit assumption that the test data is somehow similar compared to the training data. But this might not be true. Good, let's run all of that again and let's see. And now we have a split. As you can see, we have now our test data and we have our training data, which is a larger data set as intended. So that is looking good. We have a test and training set for our outputs. So that I think is quite a good start. What we could do now is we can simply print out a few labels and just check. So that is just in our Y array. I just do the np bin count, which is quite useful, and I do now the same as well for my training and test data. It's just to make sure that this actually really worked in this case. And here I refer to our train. Maybe first let's do that. Refer to our training data, and let's do the test data here. It's just to make sure that it's all done consistently. And as you can see, when you look at the whole sample, you have a 50-50-50 split according to the labels. Of course, now 70% is in your training data, so you have a 35-35-35, and then 15-15-15 in your test data. So if you don't specify the stratification, you would not ensure that these categories are the same in terms of proportion. So that is, you see now, if you run it again, it would be a little bit different, which is more challenging for the algorithm. Yeah, but of course it's perfectly fine to also test that as well. In fact, I would actually try both and see how that works. But for the time being, we impose the rule that we want to have the same proportions. Next, we have to standardize our inputs. Now, this is quite a common step in machine learning tools to standardize the input data. So what you do is you take your original data, so this would be in our data matrix X, and you deduct the mean of the respective variable, and you divide by the standard deviation. So basically, in terms of equation, what you do is you take an x, so this is your variable, let's put it in brackets, you put it minus the expected value of x, and you divide by a standard deviation. So this is basically what is going on. Now, in most cases, this is a useful way of handling data. The benefit of doing this is if the random variable x, so your input, if you regard this as a random variable, is normally distributed, the standardization would ensure that you have a standard normal distribution with a mean equal to 0 and a standard deviation equal to 1. Now, of course, if it's not really normally distributed, it would still center your data better compared to the original data, but of course it would not be standard normal. There are issues with it if you just use this blindly, and again this is the warning if you use a black box like this package. For instance, if x is actually an indicator variable, so only has maybe a 0 and a 1. So for instance, if x is a measure of whether a person is self-employed or not, say, then this adjustment is not meaningful. Yeah, so you have to be very clear that the adjustment we are making here, the standardization, is meaningful in the context of a continuous variable. Otherwise, it's not meaningful. Yeah, so that's important to note. Now I introduce a new object which I call SC, and this is then standard scalar. Now standard scalar is as you can see in upper camel case, so that's a class inside my Scikit-Learn. It basically produces a class which is a standardizer, so to speak, for data. Good, so now what I can do is I can now fit my standardization. What this does is it simply would refer to the data I would like to fit. Now in our case we refer to our training data. Now that's important to note. So put differently, I do the standardization deducting the mean, dividing by the standard deviation based on what I know in my training data. So this method implicitly assumes that the test data is somehow similar. But again, warning sign, that doesn't have to be true. Okay, the next thing I do is I standardize my data. So I call the new data in the training data sets std for standardization, and I refer to my object, and then I say transform, and here I pass in what I want to transform, which is my training data. And I do the same now for my test data, and again note I standardize my test data based on my knowledge obtained based on the training data. So that's important to note. Okay, so here we are, and now we are standardized. Okay, so that is quite useful. Good. Now I show you how to train a perceptron. Of course, we developed our own code. Now, to be honest, our own code actually has some benefits because we check for errors and we stop the loop and so on. It's actually to some extent a better implementation. But now I want to use the existing implementation in Scikit-Learn. What I do is I create a perceptron object, and I then initialize it with max iteration. That's a keyword which I put at 40. I use iter, which is my learning rate. Note here the notation iter 0. That's just what they use to implement it. I put a 0.1, and then a random state. That's the random seed, and I put a 1 here. Okay, so that should actually initialize it. And then I want to fit the data, and I just use the fit method on it. And I fit the data now based on my training data, which refers to my inputs stored in the data matrix xtrain. And of course one should use our standardization. And then ytrain is our dependent variable. And note, of course, we don't standardize that because that's a classifier. Yeah, it's 0, 1, 2. Don't standardize it. Good. So that is a nice start, and we can now train it, and now we can of course check how many mistakes we make. And that's the nice thing in Scikit-Learn, it's all built in. So for instance, I could specify now my predictions, and I refer to my perceptron object, and I use the predict method on it. And I use the prediction now based on my test data. Again, I standardize that. So I use the test data to check how many predictions are correct or not correct. And then I want to put in a print function here. And I show you now one way of doing this. And I want to note how many misclassified samples are there. Actually, cases is better than samples. So misclassified cases, and I put a column here, and now I use a different method. I use another space holder %d, which is a space holder as well. And after the string, I put % to now actually tell what should go into the space. And I want to compare my test data with my prediction, so that whenever I'm not correct, so not equal to my prediction, I should pass that in and sum up over my mistakes. So this gives me the number of mistakes I make, and I will discuss this in a minute a bit more. So let me just run that and see, and I have only one misclassified case, so that is pretty good. Now if we get rid of my stratification, I suspect that that might get a bit worse. And you see it actually does. We have lots of misclassified cases. So that is a little bit of the issue here. So only if the test data is quite similar compared to what I'm used to, the method is good. Otherwise, as you can see, it's a little bit lousy. Yeah, so that's something to have in mind. So that is not really perfect. Okay, I go back and put in certification again. I run this again, and I have only one mistake. Now, a few notes here. So what I have done basically in here is I look at my two arrays. So let me look at my test data. That's an array, and my prediction is another array, and I compare them and say and ask, are they equal or not? So that should give me a boolean. Yeah, so if I run this, you get a boolean. In most cases, they are actually the same. In one case, they are not the same, and it becomes true. Now, on an array, I can use the sum method. So I can use something like you have seen above and apply a sum method, and I would get the sum of the true cases, which is 1 in our case. Now, the sum method does not work in the case of having not an array. So put differently, if I only have, for instance, a boolean like a false, let's put it in like this, using the sum is not meaningful. Yeah, so that won't work. It only works because we have an array. Yeah, the same applies to having a list. So if I have a list of false and true and maybe something else here, let's do that. So if I have a list and then I use my sum method, that again would be an issue. Yeah. So put differently, this method only works in the context of an array. Something to note. Good. We already know an alternative way of writing this is using a formatted string. So I can do the following. I put in a formatted string, I put in our placeholder here, and I pass in what we want to show. So that is another way of doing it. Honestly, I prefer a formatted string because that's more Pythonian, if you like, and computer science people and programmers would actually say this is more elegant. But there are different ways of doing it. It's nice to know different ways. In particular, if you read other people's code, you might come across different ways of showing results. Okay, so that is quite useful. Another thing we can do is we can check our precision. Of course, we already know we only make one mistake, so it's a pretty good prediction here. There is a built-in score function which you can access in our package. So I do another print function here, and I just want to also demonstrate this. I just refer here to accuracy. And I want to show this in a particular format, so that's the benefit of this notation. You put percent again for placeholder, and 2f is a fixed format, so I basically have 2 decimal places. So it gives me a formatted output, and I put here my placeholder, and I want to have my accuracy score. It's actually in here. That's pretty useful. And I want to refer to my test data compared to my prediction. So I basically compare the two. So that should give me an output. Okay. Did I forget something here? Most likely I did. Indeed I did, because I didn't close the brackets here. So that's not very helpful otherwise. So that should give me my accuracy, and well, I only make one mistake, so it's 98% precise. You can also go into the scores as well. A different way of doing that is to refer to my scores, and that would then refer to ppn, my object, going into this cool method, and that actually then refers to my test data and not my prediction. So it's a different way of implementing it. I just want to show this because sometimes that might be maybe a bit more useful, but it doesn't do anything else. Oops. I have to not forget my standardization. So it's not a big surprise that accuracy really drops, because I of course fitted the whole thing using standardized data, and of course once I don't use standardized data, things fall apart. So that should be fine. Yeah, that makes sense. Good. Okay, so that's pretty useful. The next thing is to visualize it. And as you can see on Blackboard, this is a very lengthy command, and it's not very smart, you know, it's just lots of work. So what I do now is I cheat a little bit and copy paste that, because it will take me otherwise half an hour to do this, and it's not really very exciting. And to be honest, when I do this kind of work, I always copy paste and recycle my code, because it's just very painful to type it all out. But that's simply just putting and plotting the results. The interesting things are already captured in our discussion. Let's run this and we get our outputs. So that is quite nice. We have now 3 different zones. We have 3 different labels compared to our previous application with 2 labels. And that's quite a nice way of plotting this. Of course, you see you make some mistakes here. But this is in your test data. In your training data, which is different, there are less mistakes. Yeah, but in general, this is a decent outcome. It's a very simple algorithm, and you're not too far off. Of course, if you remove stratification, things will get a bit worse. Obviously, it's what you would expect. Okay, so that's all for today, and I hope you enjoyed. I'll see you next time. Thank you very much.